In the complex and interconnected world of electrical power systems, few concepts are as fundamental yet as often overlooked as power system angles. These angular parameters, phase angle, torque angle or load angle, and power angle, serve as the vital signs of a healthy, stable, and efficiently operating power grid. While they may seem like basic textbook material on the surface, their implications are profound and far-reaching, influencing everything from individual generator performance to system-wide stability across entire transmission networks. Understanding these angles is not merely an academic exercise, it is essential for grid operators, system planners, and electrical engineers who must ensure the continuous, reliable delivery of electrical energy to millions of consumers. Phase angle, the local power relationship. The phase angle, typically denoted by the Greek letter theta, represents the angular separation between the voltage and current waveforms at a specific point in the power system, a single node or measurement location. This angular difference is measured from the zero crossing point on the horizontal axis of the waveforms and indicates whether the current is leading or lagging behind the voltage. For this measurement to have practical significance, both voltage and current must be measured at the same node and must operate at the same frequency, non-negotiable requirements for accurate phase angle determination. The phase angle is directly linked to the concept of leading and lagging, which arises from the reactive power characteristics of different types of electrical loads. Capacitive loads cause the current to lead the voltage, as capacitors inject reactive power and push the current waveform slightly ahead in time. Conversely, inductive loads, such as motors and transformers, cause the current to lag behind the voltage, as they consume reactive power and create a delay. This phenomenon is fundamentally driven by reactance, the opposition to current flow caused by capacitors and inductors, which differs from resistance in that it shifts the phase of the current relative to the voltage. In purely inductive or capacitive circuits, this phase shift reaches exactly 90 degrees, demonstrating the classic relationship between reactance and angular separation. The phase angle also appears in the context of power relationships through the power triangle. The angle between active power, measured in megawatts, MW, and complex power, measured in megavolt amperes, MVA, is mathematically equivalent to the phase angle between voltage and current. The cosine of this V phase angle represents the power factor, calculated as the ratio of MW to MVA. Whether viewed through the lens of waveforms or power components, the phase angle remains the same fundamental relationship at a single location, connecting local voltage and current characteristics to overall power efficiency. Core power factor, indicated by large phase angles, results in higher total current MVA for the same useful power MW, leading to increased transmission losses and reduced system efficiency. Torque angle, the internal mechanics of synchronous machines. The torque angle, also known as the load angle and typically denoted by delta, shifts our focus from points on the transmission network to the internal operation of synchronous machines, large generators and synchronous motors. This angular separation represents the difference between the rotating magnetic fields of the rotor and the stator, specifically the magnetomotive forces MMFs created by each. Unlike the phase angle, which is measured at a single point, the torque angle is an internal parameter that describes the magnetic interaction within a rotating machine, ignoring secondary effects such as resistance voltage drops or armature leakage flux to focus on the core magnetic phenomena. In a generator, the rotor spins at synchronous speed, driven by a turbine, and its magnetic field effectively drags the stator's magnetic field along, inducing voltage in the stator windings. However, the stator field cannot quite keep up with the rotor field, resulting in a slight lag. This angular lag between the rotor field and the stator field is precisely the load angle. Critically, the amount of real power the generator produces and delivers to the system is directly proportional to the sine of this load angle. As the generator works harder, delivering more power, the load angle increases, up to its stability limit, beyond which the generator loses synchronism and trips offline, potentially causing major system disturbances. The same principle applies to synchronous motors, where the angle is referred to as the torque angle. In motor operation, the stator's rotating magnetic field pulls the rotor's field along, causing the shaft to turn. The rotor field lags behind the stator field, and this angular difference determines the torque the motor develops. The torque produced is proportional to the sine of the torque angle, creating a direct relationship between the angular separation of magnetic fields and the mechanical work output. This angle is particularly important for large industrial motors and utility generators, where it serves as a critical indicator of machine stability. If the load angle becomes too large, Whether in a generator or motor, the machine loses its electromagnetic coupling and synchronization with the grid, leading to potential equipment damage and system instability. Power angle, the system-wide perspective. The power angle represents the third and perhaps most fundamental angle for understanding how power flows through the entire transmission network. This angle measures the angular separation, or phase difference, between the voltages at two different points nodes in the power system. While the phase angle relates voltage to current at a single location, and the torque angle relates internal magnetic fields within a machine, the power angle connects different locations on the grid, providing insight into how power moves from generators to loads across the transmission system. The power angle is critical because it dictates the direction of active power (MW) flow between adjacent buses. Active power naturally flows from the node with the higher power angle to the node with the lower power angle, much like water flowing downhill due to gravitational potential difference. This angular separation acts as an electrical potential gradient for active power, telling the megawatts where to go. Furthermore, assuming voltage magnitudes remain reasonably stable, the amount of active power transferred between two adjacent nodes is proportional to the sign of the power angle between them. This relationship means that power flow can be controlled by managing these angular differences, which is fundamental to the operation of power systems. Interestingly, the power angle and the generator's load angle are intimately connected. The internal load angle of a generator, separating its rotor and stator fields, effectively sets the phase angle of its terminal voltage relative to the rest of the system. Therefore, the angular difference between a generator's terminal voltage and the voltage at the bus it connects to is essentially its load angle appearing externally. In practical terms, a generator's power angle relative to the next bus equals its internal load angle. This connection helps explain why the internal machine dynamics have such profound implications for system-wide power flow and stability. The power angle is primarily responsible for active power flow, while reactive power (MVAR) flow is more sensitive to differences in voltage magnitude between buses. Understanding this distinction is crucial for grid operators, as active and reactive power flows are controlled through different mechanisms: active power through angular differences, reactive power through voltage magnitude variations. The power angle's role in determining power flow direction and magnitude makes it the most important angle from a system-wide operational perspective, directly influencing how effectively power can be delivered from generation sources to load centers. The critical importance of angle monitoring and measurement. Beyond their theoretical definitions, these three angles are absolutely vital for the day-to-day operation of power systems. They serve as the core indicators of system health, performance, and stability, parameters that engineers and operators constantly monitor and manage to ensure reliable electricity delivery. The power angle is particularly critical for assessing the overall stability of the entire system, determining whether the grid can ride through disturbances such as generator trips, line outages, or sudden load changes. Phase angle monitoring is essential for managing power factor locally, which in turn involves optimizing reactive power compensation to improve efficiency and reduce losses. The torque load angle is vital for maintaining the stability of individual generators and large motors, preventing loss of synchronism that could cascade into system-wide failures. The monitoring of power angles has evolved significantly with technological advancement. Historically, power system operators relied on state estimators using SCADA, supervisory control and data acquisition measurements. However, this approach had fundamental limitations. The measurements were asynchronous, with different time stamps from various locations, and the update rates were slow, typically one update every 1 to 5 minutes. This made it nearly impossible to obtain a true simultaneous snapshot of angular conditions across a large transmission network during dynamic events, severely limiting the ability to observe fast phenomena such as power oscillations or angular swings. The revolutionary solution came in the form of GPS-synchronized time stamps, enabling synchrophasor technology through phasor measurement units (PMUs). These devices provide perfectly time-synchronized measurements of voltage magnitude and angle at multiple locations, using the GPS signal as a universal time reference. This allows meaningful comparison of angles measured at substations hundreds or thousands of miles apart, providing unprecedented visibility into the grid's dynamic angular behavior. PMUs offer dramatically higher data rates, 25, 50, or even 100 samples per second, compared to the minute-scale updates of state estimators. This technology forms the backbone of Wide Area Monitoring Systems (WAMS), enabling operators to see oscillations, angle swings, and dynamic events in near real time that were previously invisible. Power angle monitoring is typically divided into two categories: adjacent node monitoring and wide area node pair monitoring. Adjacent node angle monitoring measures the angular difference between directly connected points, such as the two ends of a transmission line. This is critical for local system stability because smaller angles between directly connected points indicate stronger synchronizing torque. The electrical force pulling generators are sections of the grid together and keeping them locked in step. Operators typically aim to keep adjacent angles below 30 degrees under normal conditions to ensure adequate stability margins, with more restrictive limits applied during equipment outages or N1 contingency conditions. Wide area node pair angle monitoring examines the angular separation between geographically or electrically distant points, potentially across different control areas. These angles are less about direct synchronizing forces and more about assessing overall system stress levels across larger regions. Unlike adjacent angles, there are no specific rule of thumb limits for wide area angles, as they serve more as trend indicators. High wide area angles might indicate excessive power transfer across transmission paths or weak voltage support in intermediate regions, while low angles could suggest reduced power flow or improved voltage profiles. Operators interpret these angles in context, setting thresholds and alarms based on their understanding of system behavior patterns. Angles is the language of grid health. The three power system angles, phase, torque, and power, are far more than abstract mathematical concepts. They are the language through which the power grid communicates its condition, health, and operational status. Understanding these angles provides insight into everything from local power factor efficiency to generator stability to system-wide power flow management. They enable operators to gauge system stress, assess stability margins, and determine when the grid is approaching operational limits that require intervention.